right, practice exercise 54. Practice exercise 54. Where will be today?
Muchos gracias.
Practice exercise 54. Similar to our last practice exercise in that we're going to be working with signed numbers. We worked with adding and subtracting. We'll work with multiplying and dividing today. No calculator, definitely should not need it. Should be a very quick practice exercise. Exercise 54. And you may, come on Ethan, begin. Here's your 1 through 8, and you're working on the identify here, not those ones the calculator. Correction. Sorry, section 2 if you the other ones up here. Or you can do section 5. I lied. We're still in the part you can roll lesson 4, just a reminder you don't have the courage and undo. He'll mention it not in this class, since you've already gotten US. All right, let's take a look at these together. And Jamie was first. Jamie, going across the top row, what did you get for your answers?
24.
Good.
Negative 24.
Yep.
72.
Good. Positive 24, negative 24, positive 72. Next row.
Negative 44.
Yep.
Negative 14.
Oh, all right, let's go to Chris. Did you get negative 44 for the first one?
Yes.
What did you get for the next one?
0.
0. Yeah, that's one of those kick yourself moments, isn't it?
Yeah, okay.
Yeah, 0. And then for the last one on that row, Chris?
Negative 720.
Negative 720. How many got gotten on that one? How many got this? You got the 0. You did it correctly. Okay, some of you got gotten by the 0. Remember, anything times 0 equals 0. All right, we go to the bottom section now. Chris, we're staying with you. That first row of division problems.
7.
Yep.
Negative 3.
Mm-hmm.
Negative 5.
Yep.
6.
Yep.
7.
Yep.
Negative 8.
Good. 7, negative 3, negative 5, positive 6, positive 7, negative 8. Next row.
8.
Yep.
Negative 7.
Yep.
Negative 9.
Yep.
5.
Yep.
12.
Yep.
4.
Sometimes
it feels
Great
bad.
job.
It feels bad winning so much. It's so bad. It feels bad winning so much.
All right. No comment. I wouldn't know what it feels like. I'm a Notre Dame fan. All right.
You're also a Colts fan. That's tough.
It is a tough combination. Love it. Anyway, anyone else get them all correct, just not as fast? All right, good job, Quentin. How many of you just missed one?
0.
That was the 0 problem. All right. Questions on any of these? All right, pass those forward if you would, please. And go and take your homework out. Turn your books to page 147. Books out, open to page 147. And let's go and review over some things we talked about recently. Of course, we talked a lot about tangents. What is a tangent, Ethan?
A line that touches only one point of a circle.
A line that touches only one point of a circle, or intersects a circle only once, touches a circle at but one point. something along only one point of contact. And we said that when we think tangent, we need to think, Kendall, perpendicular, because a tangent is always going to be perpendicular to a, or at the, very good. Tangent is perpendicular to radius or diameter at the point of tangency. Now, at a particular point on a circle, how many tangents may be drawn, Chris? Only one. From a point outside a circle, how many tangents may be drawn to the circle, Audrey? No. Two. So from a point outside, you can draw two tangents. At a point on the circle, you can draw one. How about through a point within a circle, Jamie?
Within a circle?
How many tangents may be drawn to the circle?
One.
Genesis? Chris? She just said that. Zero, because if it goes through the circle, it would intersect a second time. So you can't draw any tangents within a circle.
I heard that. I'll guess.
Make sure we're paying attention. He's trying to answer the question without even hearing it. What did the Bible say about that? He that answereth the matter before he hear it is a folly and a shame unto him? Something like that. Anyway, better to say, what? Shame, shame. And you're a Ravens fan. Wait, never mind. They won. All right. If a line is perpendicular to a radius at its end point on the circle, Audrey, then if a line is perpendicular to a radius at its end point on the circle, then that line is, Quentin, tangent to the circle. So if it's tangent, it's going to be perpendicular at the point of tangency to the radius. If it's perpendicular to the radius at the point of tangency, at the point on the circle, then it's going to be tangent. If we had two tangents drawn to the same circle from some point outside the circle, Audrey, for redemption, third tries the charm. Two tangents drawn to the same circle from a point outside the circle. You already got that one. Let's come to Genesis. Jamie.
They're equal?
They're equal. Good. Tangents drawn to the same circle from the same external point will be equal to each other. Now, something you said, Audrey, you said something about equal angles? Or you said something about pass through the center. That's what it was. So we said if we did have a couple of tangents, pretending these are straight lines that are actually tangent. All right, if we did have a couple of tangents, the bisector of this angle would go through the center of the circle, but the tangent lines themselves are equal to each other. So that if I do draw a line from the center to an external point from whence two tangents are drawn, this line will form two equal angles. That was a corollary. The corollary, in fact, to the fact that these tangents are equal. So I guess if we were to draw this picture, I've got 4 different playing statements I could state. First of all, if I have tangents, class, they're perpendicular. So the fact that we've got perpendiculars is claim. But also the fact that two tangents from the same point, class, the tangents are equal to each other. But also, since there's a line going to the center, the angles are equal. And of course, anytime you have multiple radii within the same circle, they're equal to each other. I mean, so lots of clang from this picture. And again, the key really to a good proof is to identify the clang quickly up front. What if we had two tangents drawn to the same circle, but they're not drawn from the same point? Rather, they're drawn at endpoints of the same diameter. Two tangents drawn at the endpoints of a diameter. Genesis for redemption. Audrey, fourth tries the charm. It's not the charm. Ethan.
Parallel.
They're going to be parallel to each other because they're both perpendicular to the same line. If two circles are tangent to the same line at the same point, then we would describe the circles, Jamie, as being?
Tangent internally?
Well, just tangent circles in general, right? Now, if the one circle lies within the other, then they would be tangent internally. If they're tangent this way, tangent externally. A line that is tangent to two or more circles. Kendall? A line that is tangent to two circles. Chris?
A line that's tangent to two circles?
Common tangent, okay? Common tangent, should have called on Audrey that time. Of course, if the line is on the same side of both circles, then it's an external tangent. If it goes in between the circles, then it's an internal tangent. What do we call the line that passes through the centers of two circles, Audrey? Too specific? You did what Jamie did the other day. The line of centers. Line of centers. And then the portion of the line of centers that's actually between the two centers is the center segment. If two tangents are drawn to a circle, and we were to join the points of tangency, Quentin, we have drawn the? Not necessarily. So we've got a circle, we've got a tangent, we've got some other tangent. So here's 2 points of tangency. We join the points of tangency. It could be a diameter, I suppose, if the tangents were parallel. But just in general, it's called the Genesis. That is a term, but it's not this one.
Line of tangency.
Not line of tangency. Anyone? Chord of tangency. The chord of tangency. Now, the common chord, Genesis, would be formed if two circles intersect each other, right? Then we're going to have these 2 points. They're not formed by tangents, but rather by two intersecting circles. Then this line would be the chord, the common chord. So chord of tangency is drawn between two tangents. Common chord is drawn between two circles, points of intersections. We did state this, that if you were to draw the line of centers, and of course you have this common chord from intersecting circles, the line of centers will always be the what, Kendall, to the common chord? When two circles intersect, the line of centers will be the what to the common chord? More specifically? Perpendicular bisector. It'll both bisect and be perpendicular to the common chord. We also said this, that if you were to draw a circle, and then using the same center point but a different radius, draw another circle, so that these two circles share the same center. We would describe these circles, Genesis, as being not inscribed. That would require, something like, chords or something, or perhaps tangents drawn to one of them. That would give you an inscribed circle. But if two circles share the same center, we describe the circles as being, class? Concentric. Okay, this was the last term I gave you right as we were dismissing class, because it actually, your proof involved concentric circles. So how do we describe these circles again, Genesis? Right, circles that share the same center are called concentric circles. Good. And you actually see that picture there on page 147. They give you an illustration of concentric circles as well, with a little picture of a water droplet hitting a puddle and the ripples coming out being concentric circles. I give you the example of a bullseye or a target. Technically the target, not the bullseye, that's just the center. But anyway, a target being an example of concentric circles also. Alright, so tell you what, Genesis, if you would read problem number 5 for me there on page 147. Let's take a look at your homework proof.
Prove that if a line cuts two concentric circles, and the segments of the line intersected between the two circles are equal.
Alright, so you had to give yourself the picture this time. Let's see how we do this. First of all, if you would hold up your proof so that I can see that you did complete it. Good, looks a little short. And I suddenly got something in my eyes. I was trying to look at Audrey's. Let's try that again. Did you draw an angle or did you draw one continuous line? Okay, it did say one line cuts through, so the picture was a little bit off. Did you copy Audrey's work? You just somehow thought the same thing? Yeah, a single line cuts the concentric circle. So most of you got that for the picture. So you two specifically, maybe turn the paper over. Let's do this on the back. So we should have started by drawing a couple of concentric circles. And the way we'll name concentric circles, we didn't have a chance to go over this in class the other day, is you'll name the one center point. We could, for instance, name it O. And the circles then would be O and O prime. But you only label the one point, because there is only one point. But they can't be circle O and circle O, so to differentiate them, we'll use the prime notation. So again, I don't blame you at all for not having this. That said, I don't know that it was super critical to have this in your given, but you're given circle O and circle O concentric circles, circle O and circle O prime. And we should have had a line, and I'm going to use a single letter to name the line. Let's just name it L. L intersects circle O, and let's name these 2 points. I'll just call them A and B. And then it also intersects circle O prime, and let's call these points C and D. You could have named them whatever you had. Now, if you didn't have all of this detail, that's actually not that critical, as long as you have the correct picture with 1, 2, 3, 4 points in question. All right? So 4 points of intersection there at C and D. All right, what we want to prove, and this is what's really important to get in the prove, we're trying to prove, it says, that if a line, L, cuts 2 concentric circles, O and O prime, then the segments of the line, the pieces of the line, intercepted between the 2 circles are equal. What 2 segments are between the 2 circles, Genesis?
AC and DB.
Good, we want to prove that AC and DB are equal. How many of you who had the single line cutting through identified that these little pieces are what we were trying to prove equal? All right, good. So let's go ahead and get down our, if you didn't, go ahead and fix it now. 2 statements. Statements, reasons. There we go. Statements and reasons.
Would you have used a vertical line as well?
You could, yeah, any line could have worked. You did not have to be horizontal, as long as, you know, I mean, if I'm looking at it this way, as long as this segment and that segment were the segments we're trying to prove equal.
How many steps was this proof supposed to be?
We're about to find out. All right, so given concentric circle O and circle O prime, L intersects circle O at A and B, and circle O prime at C and D. So you want to tweak your given a little bit if you didn't have that down. Modify your given just a little bit to make it reflect something like that. You keep your own point names or circle names, but modify it to match yours. So if you called your circle J, okay, then circle J and J prime. Whatever you named your L is fine as well. Whatever you named your line, excuse me, is fine. Whatever you named your points is fine. But make your given mirror mine, just with the letters that you already used in your picture. Of course, Audrey and Kendall, since you're redoing the picture, you're certainly free to use the lettering I used. All right. Once we've got that, there's no clang at all.
Nice. I feel like there should be clang for concentric. We just have a wondering what.
Concentric, I mean, just means the same center point, but that's really meaningless to us here, other than how to draw the picture. So we're going to have to do the entire proof analytically. I'm trying to prove that 2 line segments are equal to each other. This piece and that piece. Thoughts on how we could prove this? I'm going to go to Kendall and Audrey first, since they didn't have a chance to think this through earlier, since they had the picture a little bit off. Ladies, thoughts on how we could try to get these 2 segments equal to each other? Considering we have no clang at all, this doesn't look good, right? Maybe as we look at the picture, like, man, if only there were some more lines on it, right? I mean, that would help. Wait, thoughts then, Kendall?
Draw.
What lines might we draw, Kendall? Okay, so like which ones? Or ones, or whatever. Okay, so maybe if we draw OC, maybe that could help us a little bit. Okay, again, it's technically, I guess that'd be O prime C and O prime D, because that's a smaller circle. But yeah, maybe drawing a couple lines like that. Any other lines you want to draw, or we think we're good with those? we're good? All right, so number 2, we could say draw O prime C and O prime D. Reason, Kendall?
2.6
Audrey, do you think there's any merit in drawing these lines? Do you think these lines could help us? Do you think maybe we should have drawn different lines, or should we draw more lines? What do you think? Do you agree with Friend, or do you think it should help Friend? Can they hurt us? I mean, more lines is more lines, right? Yeah, I'd be inclined to go and do OA and OB as well. So let's go and draw those also. So draw OC, O prime C and O prime D, and OA and OB. And same reason, right? 2 points determine a straight line. Now, Kendall, let me come back to you. By drawing O prime C and O prime D, you formed a triangle. But when Audrey had us also draw OA and OB, we actually formed triangles. Ah, triangles. Let me leave the ladies in the back alone now. Put them on the spot now. Genesis, let me come up to you. Triangles. Does that suggest any way to get these two little segments equal to each other? So you're thinking maybe if we could get the triangles congruent, that could help me, right? What triangles would need to be congruent here, Genesis? Triangle AOC, this little tiny thing over here, this insignificant nothingness that we call AOC. Oh, sorry. And then, yeah, BOD. Triangle BOD. Sorry, I got a little political there. Yeah, if we can get triangle AOC and triangle BOD congruent to each other, it just lends itself, like with the letters we use in geometry class, you know. I never had these jokes. 2 years ago, these jokes didn't exist. It's, you know, she's actually been a blessing for my geometry class. Anyway, we'll stop there. So yeah, if I could get the triangles congruent, do we all agree if, and I don't know that we can, but if we could get these triangles congruent, then AC and BD would be equal by, just that, how many that did set the picture up correctly? You tried this. You drew your radii and you tried it.
Completely different. I don't think it worked.
I'm not sure that you can do it differently from this.
Well, I do my line through the center.
Me too.
Oh.
I have a question.
I did too.
I have a question.
Now, did it say, okay, let me pause there and say this for the video's sake. If you drew your line through the center, this proof is very easily manageable, right? Set the two big radii equal to each other, the small radii equal to each other, say that the whole is equal to the sum of its parts, subtract equals from equals, remainders are equal. But did it say that it goes through the center?
But did it say not?
Hold on, that's not the way you interpret it, because unless it specifies, your method of proof can only work if it goes through the center. My method of proof works no matter where it cuts through. Does that make sense? And that's the reason why, I've said it before, do you remember this? Unless it specifies this, don't draw it that way. Right? Does it say it's isosceles? No, then don't draw it isosceles. Does it say it's a right triangle? Okay, then don't draw it a right triangle. Does it say it goes through the center? Then don't draw it through the center. Does that make sense then? But yes, yeah, the proof would be very easily doable if they'd said the line went through the center. We're going to prove whether it does or not, then it would still work. All right, so that means, so nobody did this. Everybody's line went through the center of the circle.
I didn't go
No, okay, so all y'all are pretty much back in the same boat now. I've been picking on these girls. Y'all's pictures were better, but not perfect still, because you drew too specific. And a lesson we can learn from that too, and that's not a bad thing. All right, so how then, since nobody did this, could we get these triangles congruent? What are your thoughts? Chris?
Well, how can we get them congruent?
Yeah, thoughts on, because we all agreed if we could get them congruent, which is what Genesis proposed, then the lines would be equal by CPCT. So she had a great idea. We just got to figure out, can we make this happen?
How can we get them congruent?
How could we get them congruent? Yes, yes.
Or is ASA, SAA, is that what you're asking?
Okay, so we got, you said ASA,
Side angle side.
side angle side, side. Well, okay, keep going.
And side angle.
Side angle. Now, one of these we could rule out because we're trying to prove these two sides equal, right? So that means one of these obviously can't work, class. Side, 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 right? Because if we had side, 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 we'd already have the sides, and then we wouldn't need the congruent triangles. All right, so are there then, the next question comes, obviously then for congruency you need sides and angles. What sides, well, you know what? It might help if I numbered some angles, wouldn't it? I'm going to call this angle 1. I'm going to call the obtuse angle here, I'm going to call that angle 2, 3, 4, 5, 6, 7, 8, 9. Do you see it?
Why can't we say AO equals BO?
We haven't said that we couldn't say that. I was just numbering some angles real quick. All right, so we need to get some angles equal, well, actually, we need to get some sides equal. What sides could we get equal? Chris.
AO BO.
Right, we could get AO and BO equal
And
because.
CO, right?
I'm sorry?
AO BO and CO DO, right? No, DO and CO won't work. No.
AO and BO, yes.
Or equal.
DO or
But
CO.
CO,
And-
CO equals DO.
CO prime and DO prime, right? Because O prime's the
Yeah.
little circle. Yeah, so AO and BO have to be equal to each other.
And we already have it.
And, hold on,
Wait, no, we
and CO prime and DO prime have to be equal, right? Because, class,
Or is that in circle? Or
Are
in
equal.
a circle or equal?
alright, so far that gives me, in the triangles, these sides are equal, and these sides are equal. So I've got a couple sets of sides right here in number 3. We already said side, side, side is out, so that means it all comes down to, class, getting some angles, right? Okay, Ethan,
3 equals O.
what angles might we get equal?
One is.
Okay, angle 1 and angle 6. How are angle 1 and angle 6 equal to each other, Ethan?
Because it's two sides equal, and that's a whole triangle.
Right, if you're looking at the big triangle, AOB, we've got equal sides, equal angles, 1 and 6. How would we word our reason here, Ethan?
Opposite equal angles. Well, we have another small opposite sides and
Angles,
opposite equal sides of a triangle.
there we go, angles, we're trying to prove the angles are equal, so angles opposite equal sides in a triangle are equal. So that would get us 1 and 6. There's a set of angles, all right? So what do we have now?
SAS.
Careful.
No.
Here's the sides. It would have to be 7 and 9 for side angle side, wouldn't it? What do we have, class? Side, side, angle. And is side, side, angle a way to prove triangles congruent?
What if we get 3 and 5? That still wouldn't work?
3 and 5?
Yeah.
How would you get 3 and 5
Yes.
equal?
3 sounds
3 looks very
You
acute,
mean
5
2
looks
and
very
5.
I can't really
obtuse.
read the angles. What if,
2 and 5.
what, so, I can't read the angles. So,
So
there-
it's 1, 2, 3, 4, 5, 6, 7, 8, 9 at the center.
4 equals 2? Is that would be the corresponding thing too? 2 and 5?
2 and 5, these two right here,
Mm.
or 3 and 4 here, 7, 8, 9 here.
That's what parallel lines, by the way.
Do we have parallel lines?
Nope.
No.
No, we don't have parallel lines.
What about, 3 and 4? Might as well get all
3 and 4, well, and aren't 3 and 4 equal, class, for the
Yes.
same reason? So yeah, angle 3
Same.
and angle 4 are also equal because inside little triangle CO prime D, right? CO prime and DO prime are equal, so angle 3 and angle 4
So are 1 and 5.
have to be
So
equal.
2 and 5.
Wait, so would 2 and 5, hold on.
When?
Why would 2 and 5 be equal, Quentin?
For the same reason.
Are these two angles opposite equal sides in the same triangle? No. 1 and 6 are in the same big triangle. 3 and 4 are in the same little triangle here. 2 and 5 are definitely in 2 separate triangles, aren't they? But,
OB and OA are equal.
right, OB and OA are equal, that's true.
Those two angles are opposite equal sides.
But they're in 2 different triangles, right? Angle 2 is in triangle AOC, and angle 5 is in triangle BOD. Right? And they need to be, as I've told Chris a number of times this year, in the same triangle, right? Your turn.
What about sides opposite equal angles?
In the same triangle.
Alright, may I be excused, please?
No, you may not. Does it help me that 3 and 4 are equal? I mean, are they even in these two triangles? Because these are the triangles in question, right? 3 and 4 aren't even in those triangles. Does having 3 and 4 equal help me?
If we get CD equal.
Is that something to do with the external angle?
Okay, there's a thought. There's a number of ways we could have gone with the statement, with the question I asked. But 3 and 4 are what kind of angles?
External angle.
Exterior angles,
Exterior.
right? What do we know about an exterior angle, class?
They're equal.
They're greater or
Greater than opposite interior angles, right? What else do we know?
they're
Equal to the sum.
Equal to the sum. Well, wait a second. That means, for those who can actually read the picture, which is kind of small, I give you that,
Ouch.
angle 3 is equal to what? 1 and 7, correct? Because an exterior angle of a triangle equals the sum of the opposite interior angles. What's angle 4 equal to? 6 and 9, correct? Let's go ahead and follow this line of thought. It's not the only way to do it, but it could work very nicely for us. Number 5, an exterior angle equals the sum of the opposite interior angles, right? And so if 3 and 4 are equal, and 3 equals 1 plus 7, and 4 equals 6 plus 9, Quentin, back to you, then 1 plus 7 must equal 6 plus 9 by? But if we previously stated that 1 and 6 are equal, class, then they could be subtracted away to leave me with number 7. Angle 7 equals angle 9. That's just by what again? Subtraction. Now, Chris, earlier you tried to say angle or side angle side, right? But I said that would be side angle side. We would need 7 and 9 equal. We got 7 and 9 equal. So class, now we do have side angle side. Or side, or excuse me, or you could say side angle angle. Either one would have worked here. But number 8, triangles are congruent by side angle side or side angle angle, either one. So therefore number 9, the lines would be equal by CPCTE. So a 9-step proof. I don't know that you can do it much shorter than this. Trying to think if there's a quicker way.
To be fair, this way was pretty quick though.
I mean, 9 steps isn't bad. It's not bad. It's not as good as the 5 or 6 steps y'all got when you drew your line through the center. But again, I mean, a caution, right? Sometimes you have to make the mistake to learn from the mistake. Don't assume something that's not specified in a given. All right, question, Genesis?
I can't see.
Oh, can't see subtraction down there for number 7? Was the reason? All right, questions on this. All right, let's look at some questions, by the way, in your textbook there. You're all on page 147. Some questions that are a little further up on the page. It says, can 2 intersecting circles have the same center?
Where is this?
Question number 1, we're on page 147, right? We just did number 5, so we're going to look a little further up in this same section.
Oh, I see.
It says, can 2 intersecting circles have the same center? Jamie, what do you think?
Intersecting circles?
The intersecting circles ever have the same center?
No.
No? Because if they had the same center, right, so you have these 2 intersecting circles, if the centers were the same, they wouldn't intersect anymore, right? Unless there's one exception. Can anyone think of the one time?
Draw the circles on top of each other, they're congruent.
If they were congruent, now how many times do the circles intersect, class? An infinite number of times. So if the circles intersect an infinite number of times, then yes, intersecting circles could have the same center. But generally speaking, no. Unless you have that one exception, no. Intersecting circles can't have the same center. Okay, so building on that, then could 2 congruent circles be concentric and not coincide? Genesis. Could congruent circles be concentric but not coincide? No, they'd have to, right? I mean, if you have the same point as center, concentric, and the same distance as radius, congruent, they would have to coincide on top of each other. So no, if they are congruent and they are concentric, then they will coincide. Number 3, we're not going to actually prove it, but read the question for us if you would there, Kendall.
Prove that the radii of 2 circles drawn to the points of tangency in common tangent are parallel.
Read that one more time a little louder for me.
Prove that the radii of two circles drawn to the same point of tangency and a common tangent are parallel.
Prove that the radii of two circles drawn to the points of tangency of a common tangent. Okay, so we've got two circles, and we've got a common tangent. Now, it didn't specify, Kendall, internal or external, right? Could be either one, so it's your choice. Internal, okay. So we have a common internal, pretend it's a straight line. We have a common internal tangent, right? And it says the radii drawn to the points of tangency. So there's a single radius that you could draw there because 2 points determine a straight line. There's a single radius we could draw here. It says prove that those radii have to be parallel. Kendall, we're not going to do the proof, but talk through. How would we show that those radii have to be parallel?
You have perpendicular because of tangent.
Good, because they're tangents. We know that radii are perpendicular to the tangent, okay? So you said they're perpendicular to the tangent.
And they're perpendicular to the same line.
So therefore,
They're
parallel. There we go. Lines parallel, perpendicular to the same line, are parallel. How many think of the same thing Kendall said? Number 4, go and read this for us again. We're not going to prove it, but read it for us anyway, if you would, Quentin.
Prove that two concentric circles, all chords of the one circle that are tangent to the other circle are equal.
Huh. Read that again for us, Audrey.
Prove that in two concentric circles, all chords of the one circle that are tangent to the other circle are equal.
Are y'all getting a mental picture here? Read it one more time for us, Ethan. Be thinking about the mental picture as he reads it.
Prove that in two concentric circles, all chords of the one circle that are tangent to the other circle are equal.
All right, so you get the idea. We've got two concentric circles. Pretend these are circles, okay? And we've got chords of one that are tangent to the other. So they must be chords of the bigger so that they could be tangent to the smaller, okay? So in other words, we've got a chord that's tangent. We've got another chord that's tangent. We've got another chord that's tangent, right? It says prove that any chords that are tangent to the smaller have to be equal. Why would they have to be equal? I'll open the floor. Thoughts? Jamie?
Because they're all the same distance away from the center.
Perfect. Because in this circle, all the radii are equal, correct? And if all the radii are equal and all radii are perpendicular because these are tangents, then these are also distances, right? And if they're equidistant from the center, they are equal to each other. Great job. By the way, if a line is drawn, this is a refresher for you, if a line is drawn from the center of a circle perpendicular to a chord, again, picturing the big circle now, then it will bisect. So we also have bisected pieces of tangents, don't we? Okay. Questions on that? Questions on that? All right, clear desk except for a clean sheet of paper and a pencil. Clean sheet of paper and a pencil, everything else away. Trust you studied over pages 142 to 147. I did admonish you to do so. I did not specify you would have a quiz, but I think that went without saying. At least it would have if Chris hadn't said. But I don't think it's a surprise to you to have a quiz today. So clear your desk except for sheet of paper, pencil. First, I'll see you at the top of your paper along with today's date, which is a 1/11/21. 1/11. All right? 21. Pinch your finger. 1/11/21. Pass that back. Pass that. Pass that. All right, let's go and take a look at the quiz together. Questions 1 through 9, pretty straightforward. You're going to complete each of these statements. Some of these answers will require more than one word. Okay, so be prepared to write a few words, perhaps, for filling in each of these blanks. Then for 10 through 13, if this were in a proof, if this picture were given 4 synthetic statements, you don't have to give me the reasons with them, but 4 synthetic statements you would make, don't use the identity principle. I don't want PA equals PA, OA equals
Oh,
OA,
okay.
OB equals, no, we're not doing identity. Other than identity, for synthetic statements. Yeah, you wonder why is that there? I had one do that once.
I'm not doing it.
Yeah, we're not doing that. All right. So for synthetic statements other than identity principle you could use on numbers 10 through 13 are your 4 statements. All right, you may begin. If you're watching on YouTube, I'm putting the homework on the chalkboard.